Watch this. Half the letters in this sentence are missing, and you read it anyway. That shouldn't be possible. If you took half the bricks out of a wall, the wall falls down. So what property does language have that lets your brain pull this off? The only possible answer is that the missing letters were predictable. Your brain didn't actually need them, the surviving letters already implied them. Which means a huge chunk of every sentence you've ever read was technically extra. So the real question becomes, how do we measure how much is extra? For that, we first need a way to measure information itself. Here's something crazy. You can rip out 3/4 of any English sentence, and your brain will still read it. That sounds impossible, but it's a mathematical fact. In this video, we're going to prove it, step by step, with the actual math. And by the end, you'll see why your brain, Wi-Fi, ChatGPT, and even encryption all work for the exact same reason. Imagine I'm thinking of one letter from the alphabet, and you have to figure out which. The catch, you can only ask yes or no questions. What's the smartest first question? Not, is it A? That almost always returns no, and you learn almost nothing. The smartest question splits the possibilities in half. Is it in the first half of the alphabet, A through M? Yes. 26 possibilities have collapsed to 13. Half the world, gone. Ask again. Is it in the first half of those? Yes. 13 becomes 6. Keep halving. After enough questions, only one letter is left. The number of halving questions you needed is how much information that letter carried. We call each question a bit. 2 possibilities, 1 bit. For possibilities, 2 bits. 8, 3. 16, 4. Every new bit doubles what you can pin down. So for 26 letters, not 4, that only covers 16, not 5, that covers 32. Somewhere in between. The exact answer is log base 2 of 26, about 4.7 bits. That's the maximum information a single letter could carry if every letter were equally likely. But letters aren't equally likely. E shows up in about 12% of English text. Z, barely at all. So when an E arrives, you weren't really surprised, you half expected it. When a Z arrives, you didn't see it coming. That's the second piece of Shannon's idea. Information equals surprise. A predictable letter barely surprises you, so it carries few bits. A rare letter shocks you, so it carries many. Specifically, the information from one letter is log base 2 of 1 divided by its probability. Plug in E, probability 0.12, and you get only about 3 bits. Plug in Z, probability 0.001, and you get nearly 10. The smaller the probability, the bigger the surprise, the more bits. Now we have a problem. Some letters carry a lot of bits, some carry almost nothing. What's the average information per letter? Shannon's trick, multiply each letter's surprise by how often it actually shows up. Then add that up across all 26 letters. The result is the average surprise per letter. That number has a name, entropy. The formula looks scary, H equals negative sum of P times log P, but every piece you've already seen. P is each letter's probability, log P is its surprise. Multiply and add. The minus sign just keeps the answer positive, because logs of probabilities are negative. Plug in real English letter frequencies, do the sum, and you get about 1 bit per letter. Just 1. Compare that to the maximum we found earlier, for 0.7. Of the 4.7 bits each letter could carry, real English uses only 1. 3/4 of every letter you read, every word, every sentence, every book, is, by Shannon's math, completely redundant. That's why you could read the broken sentence. Your brain used the 1 bit of real information from each letter to reconstruct the missing 3/4. So is language wasteful? Actually no, that waste is what makes language work in the real world. If a cough drowns out a syllable, the redundant letters around it tell you what got lost. If your phone signal flickers, the message gets through. Redundancy is built-in error correction. The same exact trick that keeps Wi-Fi, phone calls, and streaming working in noisy environments. The extra letters aren't waste, they're insurance. Now flip it around. If 3/4 of a text is redundant, you should be able to strip those 3/4 out and put them back later. That's compression. Zip, MP3, JPEG, all doing the same thing. Find predictable structure. Replace it with a shorter code. A plain text file shrinks to about a third of its size because, as Shannon proved, a third is all the real information there is. Your computer is constantly doing this entropy math, deciding which bits are actually necessary. Encryption is the opposite problem. You don't want predictable patterns, you want the message to look like pure noise. Old codes were broken because of exactly the patterns we just measured. E was the most common letter, there was the most common word. Codebreakers spotted those fingerprints and reverse-engineered the cipher. Modern encryption tries to maximize entropy, make every output character look equally likely. Because if there's any structure left, an attacker has a foothold. Maximum entropy means maximum security. Which brings us back to your brain. When you read, you're not parsing each letter, you're predicting them. After Q, you predict U. After the quick brown, your brain has already finished the sentence, before your eyes caught up. That prediction engine is exactly what AI language models do. ChatGPT, Claude, Gemini, they all compute the probability of the next word, just like Shannon computed the probability of the next letter in 1948. Different hardware, same math. And it all started from one question. How predictable is English? Way more than we thought. That's the strange secret, hiding in every sentence you've ever read. If this surprised you, follow Mathrix Labs for more videos like this. See you in the next one.